Okay, so let's look today at notes on 2.1. Much of what you've already covered is means I won't have to cover it. Though I want to divide today into two different sections. And the first of which is pretty much a review for you. But I just want to cover the different techniques for solving a quadratic real quick, just to highlight the four different methods. Because on our packet, you will obviously see that there are different, the very first page is a review of doing this kind of stuff. So I would want you to be able to both factor and solve a quadratic. For example, on 19 on that worksheet, you have different scenarios by which you need to be able to solve. And if you were to make all of these problems equal to 0, and if you were to ask for solutions, then you would need to be able to do that. Most of this worksheet is dealing with greatest common factors and different types of factoring to solve. However, obviously there are some other issues that can come into play here. So what I would ask you to do is to review and work this worksheet on your own, the first one, in order to be able to get yourself up to speed on that. But just real quick, let me go ahead and make sure that we have an understanding of the different techniques. Obviously, if I have a quadratic, I'm always checking to see if it will factor first. Of course, in order to do that, that means I have to make sure it's 0 on one side before I can factor it. And then I'm going to follow that usually with an application of zero product property. So, of course, the concept meaning that if I factor it, factoring it produces a product. It produces a product naturally. For example, let's say I give you this as a problem, and I ask you very simply to solve it. And obviously it does factor very cleanly, very easily. But the natural part of factoring is to produce a product. You'll notice I have something times something else. And any time you have a product set equal to 0, this is where the application of zero product comes in. You're going to set each part of the product equal to 0. And you're going to solve. Now, these solutions right here, if I ask for the zeros, then obviously what you would do is you would leave them this way. If I ask for x-intercepts, you'd be doing the same type of a deal. In that case, I'd probably want you to give them to me as ordered pairs at -2, 0 and -1, 0. You get the idea. Okay? Questions on that? Factoring real simple. So that's our first task, right? The easiest way to really do anything is to solve by factoring. The second way to be able to look at a problem is to see if I can extract square roots of some way. A typical example of that would be something like this, right? Where I notice that I only have x as being squared, so I can clearly take the square root of both sides with the knowledge that it's an inverse operation, isn't it? Whereas I'm applying something to get rid of the square. And you have to be careful here anytime you're extracting square roots or taking square roots like this, because you have the possibility of both positive and negative. It's going to branch in two different solutions. And I can put a box around that if I want, or I could actually leave my answer as both plus and -4. That would be certainly a way to do it. That is completely, entirely up to you. I do want to give you an alternative method on this, and that would be in this case, it's a form of factoring, obviously, but be on the lookout also for difference of squares. That would be a special case type of scenario. And if I, again, started with the same problem, notice that one possible solution is to go ahead and get 16 written to the other side. And then, of course, you'll probably recognize this as a factoring pattern, where I have a perfect square, and a difference. So difference of squares says I can write this as their square roots in a plus and a minus scenario. All right? Of course, as a product, the zero product property says I take each part, set it equal to 0, and solve. And it gives me the same two solutions that I would have gotten there as if I just had extracted square roots. Okay? We okay with that one? Very clear, very easily. Now, here's a scenario where I'm going to teach you something slightly new perhaps. Now, it won't be new because you'll remember how to do this. And obviously, from the standpoint of solving, you're very rarely going to use this. But I want to show the method to you because we're going to need to use complete the square to bounce back and forth between quadratic forms. And I'll cover the quadratic forms in a little bit. But there's a goal by completing the square. And it is to be able to rewrite an equation so that I can square root it. So be able to rewrite an equation so that I can square root it. Perfect example of that would be a problem that looks like this. And I'm asking you to solve for x logically, obviously. Anybody see the issue? Your first step, obviously, is you're going to look at that and you're going to want to try to factor it, aren't you? But then you're going to realize what? It doesn't factor because 20 and 1 or 10 and 2 or 4 and 5, there's no combination of those that's going to give me that middle term for that outside-inside, right? So you're going to look at this and you're going, well, crap, let's go to the next step. And usually the next step would probably be to use number 4, which we'll talk about as quadratic formula. However, there is a possibility that I could take the square root of both sides. The problem with taking the square root of both sides is that right there, right? That single x prevents me from being able to do any kind of taking the square root of both sides. However, the trick here is that I can actually do it if I will complete a square. And this is the technique that you would do. Again, in this context, you probably would choose a different tool. You would choose a different method. But I want to remind you of what complete the square. I'm going to take 20 to the other side. And I'm going to write the problem like this. You see what I'm doing? I'm going to add a number to both sides. And I'm going to add a very predictable number to both sides, which is going to serve my purpose. All right? And it works this way. Anybody remember complete a square? All right. So what number do I put in this blank? 4. I put a 4 in that blank. And the way you know that is you're always going to take that b term. You're always going to divide that term by 2. And then you're going to square that term and put it in the blank. That's the one that I use. So b is that term in front of the x. I'm going to take it, I'm going to divide it by 2, and then I'm going to square it, and I'm going to put it there. So half of 4 is 2, squared is 4. And what I do to one side, I have to do the other. Now again, this may look like I'm just, what are you doing? But here's the nice part is that actually now factors, doesn't it? That factors very cleanly into 2 of the same factors. And because they are the same factors, it allows me to write it as the quantity squared. Now you'll notice I can do what? Now I can take the square root of both sides, see, because it completely eliminates any issues with the single x up there. So this absolutely works. And you get fast at this, by the way. You get really fast at this, to where it actually is a very quick method if you can do it in your head. But if that's the case, obviously, square root of both sides. You may know what this is right here?
2 root 6.
Yeah, this is 2 roots of 6, but it's a plus and minus 2 roots of 6, right? In other words, this splits up into the square root of 4 times the square root of 6. This is plus and minus 2. So, and remember the way those radicals break down. You'll be required to do that all year long. And then, of course, if I subtract the 2, I would leave my answer here as I would just leave it like this. Those are your two solutions, where I have negative 2 plus 2 roots of 6 and negative 2 minus 2 roots of 6. There's two possibilities here. Okay? Make sense? Of course, this always happens. Whenever it doesn't factor like this, what it means is that your x-intercepts or your zeros end up being very decimally kind of things. Either that or they're unreal kinds of things. We'll talk about that. But when we end up with radicals in the solutions, that's kind of what happens. Again, this is probably not the method I'm going to choose to be able to solve my quadratics, but it is something available to you, and you're going to have to come back to this thought of completing a square when we're bouncing back and forth between quadratic forms. Again, we'll talk about that a little bit later. The last method, of course, is our friend, the quadratic formula. And the nice thing about the quadratic formula, even though we tend to hate it, it always works. It always works. I don't have. This is a one thing serves all method, and you'll remember that what it means is I can get solutions by actually taking my A's and B's and C's and plugging it into the formula. And it will tell me what values of x makes that true. And remember, we apply this just to reiterate where we get the A's, B's, and C's from, right? When I have a quadratic in standard form like this, or the general form, whatever you want to call it, if I pull the coefficients off, those are my A's, B's, and C's, and those go in. I would, if you do choose this method, and in some cases you have to choose the method, because especially for any kind of quadratic that is unreal, when you run into quadratics like this, which have no x-intercepts like this, this means that if I had plugged such a quadratic in, I would end up with negatives under the radical here. It's unreal zeros in those scenarios. And the only way to be able to really work those types of problems is to be able to use the quadratic formula and be able to deal with these i's, the unreals that pop up. So be aware that that the quadratic formula is needed in many cases, and we will definitely come back to it when we're trying to deal with the zeros of quadratics that do not cross the x-axis. All right. In other words, just because there's no x-intercepts doesn't mean there's no zeros. And we'll talk about the nature of zeros in polynomials when we get into the next unit. Okay? Any questions on quadratic formula, though? There it is. Incidentally, if I had more time, I would actually show you how to derive this. If I take this right here, and if I complete a square algebraically on this, I can derive this, which is really slick math. It's really cool. I wish I had time to do it, but if you ever want to see that, just come to me individually. All right? Any questions on any of the ways to solve quadratics? You okay with that? It seems like elementary stuff. Here's the thing when it comes to teaching pre-cal. I don't care how you solve a quadratic. I really don't. My task for you is you just give me a solution, all right? Algebra 2 is all about teaching the tools. So what I just gave you is nothing more than a review of Algebra 2 principles, correct? All right, I don't care. You pick whatever option floats your boat, right? That's the way it works. So otherwise, hey, just get me the correct answer. That's all I care about. I want to look now at quadratic forms. In order to do your assignment today, you're going to need to know these forms a little bit better. I've already told you or alluded to a form that we know as the standard form. It'll also be called the general form. And I want to make sure that I clarify something. Our textbook, the Larson, actually calls the standard form the vertex form, which I mean he actually relabels the vertex form and calls it the standard form, and which I don't agree with. So when I talk about the standard form, I am talking about the form that is actually the descending order of the variable. This is the one we get our A's, B's, and C's from. Okay, and so anytime you see a quadratic written this way, that's what we're talking about in the standard form. The thing about the standard form is that I could give you a function Let's give you an example here and show you what may be required of you in the standard form. So let's say I have a quadratic such as this, an actual function. Anybody want to identify what A, B, and C is for me? All right. A is 1, B is 6, C is 9. Very good. So if I wanted to use the quadratic formula here, I could. Those are my numbers to be able to find. Of course, I would replace this with 0 and solve in that case. Which means that if I want to find x-intercepts, obviously I certainly can I? I would simply, hopefully, factor and solve, for x-intercepts. What do you think the y-intercept is going to be here? Yeah, y-intercept here is always C in this form. It is the 9. And as long as I'm in a standard form or a general form of descending order of the variable, in any kind of polynomial, all I have to do to get it is it's always that number. It's always the last number of the chain. Okay? As long as my polynomial is in this form, it's the y-intercept is always easy. So I can quickly look at that. Here's the thing. In this form, I can get a vertex too, right? Remember the vertex, as you've already definitely seen, the vertex is going to be where it actually touches. So, for example, let's say it does something like this, right? It's the bottom of the parabola. So I can always find the bottom of the parabola out of this form. Does anybody remember how to do that? I'm curious. Aaron remembers? All right. So here's the thing. Yeah, here's the thing. My vertex coordinates can be found by doing this. By taking the B, putting a negative in front of it, and then dividing it by 2 times the lead coefficient, the A. That will always give me the X value. Incidentally, we know also that these things have axis of symmetry, don't we? And if I were to ask for the axis of symmetry, you have to give me X equals negative B over 2A. They're always the same. The axis of symmetry always goes to the X value of the vertex in a quadratic function. Okay? If I ask for the axis of symmetry and you don't give it to me as X equals something, then I'm going to count it wrong. Because axes are lines, and I would be asking for the equation of the line. That's the axis of symmetry. It's always an X equals something. Why is it not a Y equals something? Because that would imply a parabola laying on its side, and that's not a function. Very good. So our axis of symmetry is always run vertically, which is X equals something. Now, here's the trick. How do I get Y of the vertex?
You plug in 0.
I plug in what?
0.
I plug in the X value, right? Because if I find the X, that's an input, and I can always find the matching output if I'll just plug it back in. Now you'll see it written this way: F of negative B over 2A, and that implies you take this and you actually make that the input of the function itself. Okay, so that's the way you go about that in the actual quadratic type of a scenario. All right? Yes, sir.
So you're saying that once we find an X, that all we do is just input it into the
Yeah, we plug it back in. Right? So let's do that real quick. So let's say I give you this as a problem. And let's say I want to know x-intercepts. I want to know y-intercepts. I could ask that in a quadratic. I could ask that in just about anything. I could ask for a vertex out of this form. I could ask for an axis of symmetry in this form. And I could also ask for... What else would that'd be pretty much? I could ask for minimums and maximums. I could ask for increasing, decreasing, just like on our previous activity, right? I could certainly do that. My question to you is how do I approach just this much of it? Well, x-intercepts does this, doesn't it? Right? Aren't those the factors? So what is my x-intercept? x equals negative 3. Ideally, I would get that way. Right? What does that mean to only have one x-intercept, by the way? It's a quadratic, isn't it? What does that mean? That means the vertex is on the x-axis. This is a concept known as multiplicity, where I have multiple roots of the same solution. We'll talk about that later when we get to polynomials, but just be aware. I can have duplicating zeros there, and that's what that means. Y-intercept is what?
9.
Y equals 9. I prefer to see it as 0, 9, but that's okay. All right? And it always matches the C. The vertex is negative b over 2a. Negative b is negative 6 over 2 times a, which is
2.
2 times 1, which is 2. And then that gives me what? That gives me a negative 3 for the vertex, doesn't it? Now the y is the trick. So what do you do to get the y? You actually do f of negative 3, don't you? That's exactly what you do. So you would come in here and you do f of negative 3. You take the x value, you're plugging it back in. I get, that's a positive 9. This is a negative 18. That's a positive 9. Yeah, they all cancel, don't they? This is 18 minus 18. I get a 0. Would you agree? Yeah. So when you plugged in negative 3 and you got 0, what did we say that the vertex had to be? We said the vertex had to be on the x-axis, didn't we? And that just confirms, that should be absolutely no surprise. The vertex is indeed sitting on the x-axis. It is the x-intercept itself. But that's the way you can do it in this form. All right? Negative b over 2a followed by, and of course axis of symmetry is x equals whatever the x value was. So by doing negative b over 2a, you're kind of killing two birds with one stone. I do not advocate killing birds. But if you do, only use one stone. Okay? What? Not question?
Axis of symmetry will always be the x and the x.
Always match the x. Always match the x in a function. If we talked about axes of symmetry with relation to conic sections later in the year, that will change. But right now, as of now, it's always going to be x equals something. And again, do not give me negative 3 on the test. You better tell me it's a line as an axis of symmetry. All right? That is the standard form. The second form I need you to be aware of is what we call the vertex form. The vertex form. This will also be known as the translation form. As the translation form. Can't spell. The translation form. Okay? This is also what Larson calls the standard. And the reason why he does it is he's trying to prioritize this form. This is the most valuable player in our forms. And you'll recognize it right off the bat. If I take it and if I put it in this form, then this is my vertex form. All right? This is my second form, the vertex form, is this form right here. Now, what does that mean? What do you see here? The reason why it's called a vertex form is because I pull the vertex right out of the letters, right out of the form. As such an example, if I am given a quadratic that looks something like this, then notice I'm pulling the vertex right out of the form, aren't I? My vertex here is going to be 3 and 4. Notice that I'm always opposite for the horizontal, and I'm always same direction for the vertical. Which leads me to the concept of again, the shifts and transformations, and why it's also called a translation form, because it tells me how the 0, 0 origin has been translated. The vertex has been moved from 0, 0 to 3, 4 by just adding an h and a k value. Everybody see the reason why we call it that. But that's the vertex. Yes, ma'am?
Why isn't the 3 negative 3?
Why isn't the 3 negative 3? Good question. Because horizontal shifts are always opposite the sign. Vertical shifts are always same direction as the sign. Always, yeah, critical. Now, what's the y-intercept?
0, 4.
Of this one. What's the y-intercept of this one? Here's the thing. Yeah, see, here's the thing. To find the y-intercept, you have to plug in 0 for x. And solve. Is it?
No.
See, now, and this is what I need you to understand. If you plug in 0 for x and solve, that gives you negative 3 squared, which is 9. 9 times 2 is 18. 18 plus 4 is 22. The y-intercept of this is 22, or 0, 22 is an ordered pair. Ladies and gentlemen, you're going to want to take that k right there, and you're going to want to look at it, and you're going to want to call that a y-intercept. That's what you just tried to do, right? That's what you're going to try to do. That is not a c value as shown in the standard form. The k in this form is not the y-intercept. You have to plug in 0 for x and solve for y. Am I understood on that? Very commonly missed error in this form, so you have to be real careful, okay? Now, of course, we know here that A, this lead right here, is what? This is my stretch or my compression based upon to the vertical, right? So it actually, whatever happens in the function, we're going to take all the output values, the y values, and we're going to multiply it by some factor. It's a scaling of the data, if you want to say. All right? But that's my stretch or my compression there. Now, if you look real quick at your packet. No, not at your packet. I gave you a worksheet. Pull that out. This is going to be part of your homework assignment today. And I want you to see the type of problem. Obviously, if I have these kind of problems, and if I have the problem that is in vertex form, obviously I'm probably going to get all the information I can out of the vertex form. Certainly. Right? Or I am going to rewrite this perhaps into the standard form, which looks more like this, and then try to get information out of that. See, because different forms lend themselves to different information. So the ability to actually rewrite and bounce back and forth between the standard and the vertex form are very important. All right? And again, we'll address that in a little bit. But look for me right here on number 6 on your worksheet. Its graph is a parabola with vertex of 4, 8 and passing through the origin. So there's 2 pieces of information on a problem like this, right? The fact that my vertex is 4, 8 and I'm passing through the origin with the point. Now, if I see this, I'm asking for an equation, right? How do you approach this problem? Well, let's make an example of this. Let's do it a little bit differently, though. Let me change it because I want you to have that practice. Let's say that you need to give me the equation of a parabola that goes through zero, 1 and has a vertex of -2, 3. How would you approach such a problem? Okay, I'm thinking vertex form, right? Now here's the thing. If I give you this, the first thing is to make a picture. So what is the information I have here? I have a vertex here, but it tells me it passes through what? All right. You actually have a little bit more information than you think, because in a parabola such as this, if it's a equation of function, I know an axis of symmetry, don't I? I also know that on an axis of symmetry, that it has to look on the left side like it looks on the right. So I'm definitely going to have a couple of zeros of the function, a couple of x-intercepts, real ones, that are going to be, you can estimate those, can't you? You can also estimate, or you can also know the nature of A. You also know the nature of A, don't you? In fact, that it has to be negative. All right? So there's some things you can get out of the scenario just by looking at it. My question to you is how do I derive the equation? What do I give you? I give you a vertex, don't I? Which means that you're going to want to use the vertex form in this problem. You're going to have some value A, which we don't know. You're going to have an X, and you're going to have a K. An H and a K, excuse me. You're going to have an H, you're going to have a K. What is the H? What is the K? So in this case, I'm going to put in a -2 here. That's the H. I'm going to put in a K here. And of course, it's the opposite sign type of a deal here. So this becomes that, this becomes that. And which makes sense, right? Because if I'm at 0, 0, that's a left shift of 2, boom, boom. That's an upshift of 3. See what we did there? The problem is, there's the mystery, isn't it? My question to you is this. How do I know what A is specifically? Aaron.
Because they gave you a point, you can just plug in the point.
Everybody check this out. Watch this. The extra point that they gave you, good job, the extra point that they gave you is an input-output pair. It has to be on the graph. Therefore, I can use the point to plug back into the function. This is my x, this is my f of x, right? So all I have to do is take the f of x here, the 1. A is what I'm solving for. X is what? The 0 of the point that was given. So all I have to do is take the extra point, plug it back in, and solve. Now notice, if I solve this equation right now, it's going to tell me what A has to be in order to go through that point. Does that make sense? Very good. And then I'm going to, in this case, what is that? A, this is, what's 0 plus 2? 2 squared is, I'm going to rewrite this in front. 4A plus 3 minus 3 minus 3. -2 equals 4A divided by 4 divided by 4. So what is A in that scenario? It is -1/2. And what did we say about A? What did we say about A? A had to be negative, which matches our projections. It matches our anticipation of that, doesn't it? And basically, so what I usually do in this scenario, by the way, is once I have the form, I come in here and use a big eraser or something, and I just replace A with the number that I just got down here. And that's the equation that you just derived from this scenario. Make sense? Now, if I asked you to get X and Y intercepts, could you do it?
Yes.
What would you do?
For x-axis.
Well, Y we already know. Notice Y, it doesn't match the 3, does it? I told you K is not the same thing as Y.
Plug in 0 for
Plug in 0 for this, and you're going to solve for X in this, which means you'll take 3 over, you'll multiply both sides by -2 maybe, and then maybe root both sides. Do you want me to do it real quick for you? -3 minus 3. Multiply both sides maybe by, I'm going to multiply by -2. Is that okay? That gives me 6 on this side. The -2 kills the -1/2. Root. Okay? And subtract. So this gives me what? negative 2 plus and minus the root of 6. All right, so real quick, there's one more form I want to show to you, and it's called the root form. It is also known as the factored form. And here's the context. If I did give you a form such as the standard form, and if I factored it, guess what I have? I have the factored form. So here's what the factored or the root form looks like. It says that I'm going to have some a potentially, oftentimes it's just 1. And if I took those factors, I would have an x minus something and an x minus something. And usually we put r here to designate the roots of those forms. The roots of those forms. And if we reverse the process, we would take this, set it equal to 0, we take this, set it equal to 0, and it gives us the x-intercepts. So this is an important form because if I can get it in this form, it yields zeros. It yields the zeros of the function, or x-intercepts. Okay? So, the worksheet I gave you, let me show you the importance of this. What if I gave you a function that told you that we have zeros of 5 and 1, but it goes to the point 0, 1? Check this out. If I ask, for example, find an equation that has zeros of, let's use 6 and 2, but goes through 0, 1, what do you do? Well, I'm going to use the root form. Because zeros have to come from opposite factors. So I know right now, if the moment I say that these are zeros, it has to come from that as an equation. However, I need a particular a value that will perform the right stretch of this information, the right scaling for it to go through that point. You follow? How do I find out what a is? I do the same thing I just did a while ago, don't I? I plug this in for my x, this in for my f of x, and I see what a has to be in order for it to actually go through and grab that point. Now, of course, I'm going to plug in zeros in 2 places into this form. 1 minus a, negative 6, negative 2. Negative 6 times negative 2 is 12. Therefore, a has to be, a is equal to 1/12. So then, what is the overall equation? I normally come up here and just put a 1/12 in place of the parentheses. Now notice, if I wanted to multiply this out again, I could. I would have 1/12 in that case would actually be my a value in the, and notice the a value matches the a value in the quadratic form, by the way. If I didn't multiply this all out, the lead coefficient would still be the same here. It'd be 1/12. Y'all understand? So there is a duplication in what we call a here and what we call a here and what we call a in the actual vertex form. A is a in all the forms. Okay? If that makes sense. So here's what I want you to do, guys, for your assignment. Obviously, you can do this because you had that activity early in the class. Do this. Do this right here. Do this right here, this right here, this right here. You should have the information with the forms to engage these problems. And then, of course, do this. And this takes number 1 and ask for information on it. This is your homework assignment. It will be due at the first of class next period. That said, I'll go over a couple of things. But you need to have this done enough to where after I go over a few things, you're ready to turn this in for a grade. Am I understood on that?